Okay, students, in this next possibly very short lecture, we'll actually look at a very common application paradigm for least squares. Okay, so we're going to look at the problem of data fitting. We'll start with a very simple example, and we'll hopefully generalize it to put it in context into where least squares is useful in machine learning. Okay, so suppose that it's a very simple scenario. Suppose that we have a set of points, okay, meaning that you have one variable, okay, so represented on this axis as x, and you have one measurement that you have recorded for that variable as f of x. Okay, so for example, x could be your let us say your performance in the first two segments of this course. Let's say your average grade in the first two segments of this course, and f of x could be your performance in the final segment of this course. Okay, so we are trying to understand how your performance in the final segment is related to your performance in the previous two segments. Okay, typically, as typical in these scenarios, we have a lot of data points. So let's say this course was also conducted last year, hypothetically speaking, and you have a bunch of data points to compare with, right? So you have let's say last time there were 200 students who took the class, and for each of those students you have their average score in the first two segments as your x value, and the average score in the final segment as the f of x value, right? Let's just call it the y value, okay, to make it simple for each of the students. So you have xi, yi, okay, for 1 less than or equal to I less than or equal to 200. It gives you 200 points, where xi is score of student I in first two segments, and yi is score of student I in last segment. Okay, so that gives you a bunch of points, right? So basically you have a bunch of points. Let's mark them as cross on this line. Okay, so depending on what xi and yi are, let's assume you also have negative scores and whatnot. So you basically have some structure like this. Okay, well, in this scenario you would assume x and y to be correlated, so you would roughly assume that whatever points you have, they point in like this direction rather than in this direction, right? You wouldn't believe that if x is high, f of x is low, right? You wouldn't assume a negative correlation, so to speak, right? Using these terms very vaguely, but you do understand what I mean, right? So basically you would assume that your data will actually be pointing in this direction, so to speak, roughly. Okay, so now the idea is that what if I want to make a prediction for some new students in this year, right? So you don't yet know your second segments, third segment scores, but you already know your scores in the first two segments, right? So I want to make a prediction, right, or an estimation of your score in the final segment based on all that has happened in the past, right? So the past information basically hopefully gives you some idea about how the scores in the first two segments are correlated to the score in the final segment. Now my goal is to exploit that correlation and information that I have to make a prediction of a very similar nature for you, okay, for students of this batch. Okay, so here is where your models come in. Okay, your model. So first you can here assume something like this. Let's assume that y is just linearly related to x, meaning that it is like some theta 1 x1, theta 1 xi plus theta 2. Okay, or theta 1 xi plus theta 2. So this is true for all I, 1 less than or equal to I less than or equal to 200. Okay, so basically it is trying to say that I'm trying to fit this model to the data, meaning I'm trying to assume that yi, meaning your score in the last segment, is some constant times your score in the first segment. So this theta 1 represents the correlation part, how much your score in the previous segment carries over, plus theta 2, so maybe there's some additional constant factor. Okay, so what I can try to do is I can essentially try to make sure that this model, I can assume that this model represents the relationship between xi and yi. Okay, so the point is that I don't really know what theta 1 and theta 2 are. Okay, so theta 1 and theta 2 are called the parameters of the model. Okay. Now once the model is selected, the question is pick theta 1, theta 2 such that the model best estimates y from x, okay, for any students of this batch. Okay, so that's what we need to do, right? We need to pick the correct theta 1 and theta 2, right? We don't know what theta 1 and theta 2 are, pick them, right? The kicker here is that I need to pick theta 1 and theta 2 such that my estimation improves on the current batch. Okay, but I do not have any information on the current batch. I do not know yet their scores in the final segment. I only know the scores of the students in the previous batch. Okay, so what I will do is I will actually construct the error, the model error, the error in the model, okay, on available data. Okay, this is going to be something like, yi minus theta 1 xi plus minus theta 2. Okay, this is the error in the model, right? Because this is like, we'll take the square to make it, the absolute error, yi minus theta 1 xi minus theta 2 whole square, and I'll sum it over all the students in the previous batch. Okay, so I equal to 1 to 200. There are 200 students in the previous batch. Okay, so this is the error in the model on available data. Okay, so what I will do is I'll assume that theta 1, theta 2 will be picked such that this error is minimized. Okay, now what I'm doing here is I'm actually minimizing the error on the available data, on the previous batch, not on the students in this current batch. That's an important thing to understand. In particular, the key thing to observe here is that I'm making an assumption the students of this batch are going to be very similar to students in the previous batch. Okay, in on a variety of things, in the sense that if I am able to somehow find theta 1 and theta 2 such that the error in the students of the previous batch is minimized, the error of the model for students of previous batch is minimized, that also means that the error in the current batch is minimized. I'm making that assumption. Okay, so this available data is typically called training data. Okay, because that's the data which you are using to learn the parameters theta 1 and theta 2, to find out the parameters theta 1 and theta 2. Okay, fine. And I want to use the training data to actually come up with a model for the this is what you call unseen data. So unseen input, let me call it unseen input. Okay, so basically from the training data you want to decide, or you want to estimate the output for unseen inputs. Okay, inputs that are not present in the training data. Okay, fine. So what you are trying to do is you are trying to minimize, this is called the training error. You are trying to minimize the training error, and you are hoping that the similarity in the training data to the unseen inputs, the similarity in the training inputs to the unseen inputs would also mean that this error will be small even on the unseen inputs. Okay, so that's the fundamental idea. All these concepts you will go through in detail, or most of you might have already gone through in detail in a machine learning course. Okay, the point of interest to us here is that the variables are theta 1 and theta 2, right? We want to minimize over theta 1 and theta 2, and what you have here, remember xi and yi are given to you. This data is available to you. So what you have here is a linear term inside the square. It's a linear term inside the square, and it's a sum of these terms, right? So this essentially is a linear least squares problem. It's a linear least squares problem. Okay, so in effect what I am trying to do here, I am trying to effectively estimate yi as theta 1 xi plus theta 1 xi plus theta 2. Geometrically this represents a line. Okay, so what I am trying to do is I am trying to draw a line. Okay, the slope of the line is theta 1, the intercept of the line is theta 2. Okay, the slope of the line is theta 1. Okay, I am trying to pick theta 1 and theta 2 by changing the slope and the intercept. Okay, by changing the slope and the intercept, I am trying to pick theta 1 and theta 2 such that this line best fits the data. Okay, so basically I am doing a straight line fit. Okay, so that is a linear least squares problem, and this can actually be solved using our scenario. In fact, what will be the A matrix? So if you actually start from this, let's try to construct the A matrix and the the B vector. Okay, so what will be the A matrix for us? Okay, so we can actually straight away see that just by plugging in the let's write it down here. So remember the variables are theta 1 and theta 2. So this will be your variables. This takes the role of your x we have been calling in all the right, and this is going to be y1, y2 to y200. These are the constant terms. Okay, and over here, because you only have two variables, you only have two columns. Over here, and remember theta 2 just appears with a -1 term over here, correct? So that's just going to be all ones. Okay, and theta 1 appears with x, right? So it's going to be x1, x2, so on up to x1000, so x200. Okay, so this is going to be my A matrix, and this is going to be my B vector. As you can see, A is skinny here. Okay, it is skinny because we have a lot of data, right? So in general, the number of rows in A will be the number of training data points. Okay, so A is m cross n. M will be the number of training data points, so the number of students in this case in the previous batch. Okay, and n here will be the number of parameters in the model. Okay, so here n is 2 and m is 200. Okay, right. So let me ask you this question: is it reasonable, do you think, to assume that this matrix is skinny full rank? Well, we know that it is skinny. Well, is it full rank, right? If the matrix is not full rank, this would actually mean that all these xi's are equal, right? All these xi's are equal. That essentially means that all the students in the previous batch scored exactly the same in the first two segments, right? That's a highly unlikely scenario to assume, right? So in this context, it definitely makes sense to assume that this is a full rank matrix. Okay, so of course, what the solution, the least square solution to this is going to be A transpose A inverse, A transpose times the B vector. Again, you can just work out what it is. It's not very difficult here. A transpose A is just going to be a 2 cross 2 matrix, right? And we all know how to invert 2 cross 2 matrices, right? So we'll actually get a ready expression for a straight line fit. Okay, so this is how you can actually fit a straight line onto data. Okay, fine. Now at this point you might notice that a straight line fit, this is one step where we actually made in some sense a choice, right? We sort of tried to fit this model into the data. We assume that this is how the x's relate to the y's, right? And that seems like an assumption. Why should I actually use something like this? For instance, I'm fitting a straight line here. Maybe it's not correct to fit a straight line. Maybe I need to allow for slightly more complexity, and I need to fit something like a cubic, some cubic variation like this, not just some straight line fit. Okay, so maybe a better model is given by yi equal to theta theta 1 times xi cube plus theta 2 times xi square plus theta 3. So let me, for sake of my sanity, let me just with the me redo the indexing slightly better way. Cube theta 2 theta 1 xi1 plus theta naught. Okay, so let us say maybe this is a better model. We don't really know right at this point. Maybe a cubic fit is a better model, correct? So in this case also, what we can try to do is we can try to construct the training error in a very similar fashion to what we did earlier. It's going to be summation of yi minus this whole summation over here, whole square, right? I equal to 1 to 200, and try to pick the theta naught, theta 1 up to theta 3, theta 2, theta 3, such that the training error is minimized. Once again, we make a leap of faith, assume that all the unseen inputs are going to be very similar to the training input, and so on and so forth, right? All these ideas can be formalized, right? Especially this idea of training data being similar to unseen data. Usually some statistical models are at play here. Statistical models, we assume that all these data come from some underlying statistical model, so there is some similarity, and all these things can be justified in that framework. Okay, so here, how do you find these parameters theta naught, theta 1, theta 2, theta 3, right? So here, if you plug this in, once again you see that this expression over here, the y's and the x's, these are all known, right? So the fact that you're taking a cube here shouldn't scare you, because this is actually some known constant, if I may say so, right? As far as this problem is concerned, the variables are the thetas, the parameters, right? So here you still end up having a linear term inside the squares. It's just that the constants involved in the linear term happen to be cubes of some other constant. That's it, right? So you still have linearly squares. Okay, so this is an important point to understand. It becomes very trivial as you get used to it, but at least initially, even though you are fitting a cubic, not a straight line, it is still a linearly squares problem. Okay, because what matters is the linearity in the parameters, the thetas, not the linearity in the x's or the data points. Okay, so you still have linearly squares, and you can actually work out what the A matrix and all these are. So remember, here you have variables theta naught, theta 1, theta 2, theta 3, right? And you're still going to have y1, y2, so on up to y200. Okay, so here you have n equal to 4, m equal to 200, right? And what are the columns going to be, right? So you can see theta naught always appears with a 1 here, so it's just going to be, the first column is going to be all ones. Okay, it's a different order from the previous example, that's why you see a different order here, right? It's not very different. So the second column is going to be all x's. The third column is going to be the square, x200 square. Okay, and the fourth column is going to be cubes. Okay, same terms, cubes. So x1 cube, x2 cube, and so on. Okay, so basically the first column is all ones, second column is all the x's, the third column is the square of the entry-wise square of the second column, and the last column is the entry-wise cube of the second column, so to speak. Okay, so this is what the structure is going to be. This matrix is again a skinny matrix. Okay, for those of you who are aware, this matrix is such a matrix. When you have this structure, is called a Vandermonde matrix. Okay, and this Vandermonde matrix is known to be full rank so long as all these entries are distinct, right? So x1, x2, so on up to x200 are distinct, but that's for a square matrix. Okay, so if x1, x2 and x200 are all distinct, then Vandermonde matrix is going to be invertible, even if you have a 200 cross 200 matrix. Okay, fine. So in this context, once again, here you don't have 200 columns. However, you only have 200 cross 4. It's a very very tall matrix. So in this context also it makes sense to assume that the matrix is full rank, right? Because if the matrix is not full rank, what that means is that you can actually write one of the columns in terms of the other columns. For example, you can write maybe the last column in terms of the first 3 columns, just as an example, right? What that means is essentially that the last column is some combination of the first 3 columns, meaning that this entry, which is the cube of x, is equal to some combination of 1 and x square. This entry is again a combination of 1 and x square, right? That basically means that all these entries are roots of some cubic, of some quadratic. All these entries are roots of some quadratic. Okay, it's fine if you don't get this right now, but I think most of you should be able to get this, right? So let us say that the last column is so let's call it C3, right? This column is C0, C1, C2. So let us say C3 is like alpha naught C0 plus alpha 1 C1 plus alpha 2 C2. Then all the xi are roots of the cubic x cube equal to alpha naught plus alpha 1 x plus alpha 2 x square. Okay, but you know that a cubic can only have 3 roots, 3 distinct roots, cannot have more than that. That means that in this whole bunch of students there are only 3 distinct scores, right? That means in the first 2 segments all these students, all the 200 students are just in 3 groups, and each of these groups scored exactly the same. It's again very highly unlikely, so it's reasonable to assume that this column is going to be full rank. Now this matrix is going to be full rank. Okay, I'll give you a general argument why it makes sense to always assume in such context this matrix to be full rank, but for now I think this argument for this special case makes sense. Okay, once again you can just try to compute A transpose A inverse, or you can use your QR decomposition or any of these methods to find the best cubic fit. Okay, or you can also find the best so here cubic is a degree 3 polynomial. It can go up, maybe you can fit a degree 10 polynomial, maybe you can fit a degree 20 polynomial, right? So why not fit like a very large degree polynomial, right? Why not fit a degree 200 polynomial, for example, right? For one thing, when you fit a degree 200 polynomial, very formulaically speaking, this matrix may not be full rank, because the arguments that we made may not apply when you actually start having too many columns, right? Some of these x's may end up being the same, and that will just destroy the full rank structure of this matrix. Okay, well, even you can still use pseudo inverse, right? Even if it is full rank matrix, you can use pseudo inverse to get a solution to this square. So what's the issue, right? So this point, a larger degree polynomial in general will give a better fit. Okay, just to give you an idea, so let us say you have your data that is like this, that is located like this, right? If you fit a straight line, you might just get some line like this, right? But if you fit a quadratic, maybe you will get some quadratic like this, right? But if you start to fit something like a cubic, then maybe you will get something like this. Okay, if you fit higher degree polynomial, you'll actually get something like this, right? So the more increase the degree, the more it's possible for your fit, for your model to go through all the wiggles in the data. Okay, your model will go through all the wiggles in the data, right? So it will give you a better fit in terms of training error. Okay, will you better fit? Let me just modify the statement slightly. Will give a smaller training error. Okay. So then the question that we ask is, why not just pick a really large degree polynomial? For one thing, as I told you, numerically you may run into this issue that you may actually not have an invertible matrix, but more than that, more importantly, the issue here is that we cannot actually assume that this data is completely representative of all the unseen data, meaning that we cannot assume that all these wiggles are completely indicative of the students in the current batch also. To just give a very simple scenario, maybe all these wiggles are just due to noise. Okay, so maybe that you just have maybe the true value of the score for this particular student was here, okay, but it just got shifted up due to some noise. Okay, and this noise could be different for students in the next batch. Okay, so for next batch students, maybe the noise will shift the true value downwards. Okay, and in that case, you can actually see that this fit gives you a really bad estimate for this student who happens to be here. Okay, so the main idea is that we should not in some sense trust this data completely, right? When you're actually using a very high degree polynomial, you are actually trusting this data very blindly, completely trusting the data, assuming there is no noise or no error in the data, so to speak. Okay, and we are making an assumption that all the future data is going to be exactly like the data that you have seen in the training set. Okay, so this problem is called overfitting. Okay, in the sense that when you pick a really high degree polynomial, it will fit your training data extremely well, but it will not be proper representative of the unseen data. Okay, once again, all these concepts you will go through in much more detail later on. Okay, I just want to highlight some of the key issues, right? So model selection is a key concept, is a key challenge in this setting at least, right? How do I pick what degree polynomial should I pick to fit, right? You don't actually have to fit with the polynomial. You can do something more fancy. Maybe I can assume a model is something like yi is equal to log of xi, some constant times log of xi plus some constant times hyperbolic tan of xi or whatever, right? You can just make your pick. It's a more complicated fit, t2 times square root of xi. Doesn't matter, it's still going to be linearly squared because it's going to be linear in the parameters theta 1, theta 2 and theta 3. Okay, so which model to pick, right? More complicated models, that is models with a lot of parameters, are going to give you better, smaller training error, but they may perform poorly on unseen data. Okay, fine. Okay, so all these things will go on later, but main thing I want to highlight here is that your what's important is linearity in the parameters, right? Okay, so in general the problem of data fitting is considered as follows, right? So let's say you have a set of data from some set x, right? So this set x could represent the set of students as in the example that we have considered, or maybe it represents a set of images on which you're trying to do some estimation, right? And then from this set x you obtain a set of points phi of x. So let's say phi1 of x, phi2 of x, phi3 of x, so on up to phi of x. These are some representative attributes of any element of this set x. Okay, for example, if x is a set of images, phi1 x1 would represent maybe how blurry the image is, phi2x could represent how phi2x could represent how bright the average brightness of the images, phi3x could represent how much variation is there of the brightness across the image, right? Or many other parameters that you think are relevant. These are called the features. And then whatever parameter you are trying to estimate, let's say you are trying to estimate some parameter y, you assume that your parameter y is related linearly in the features. So it's like theta I phi I of x. Okay, so this is some parameter, it's called f of x. Okay, this is the assumption. Some parameter f of x you're trying to estimate is linear in these features. Okay, so the features I equal to 1 to however many data points you have in your data set. Okay, in our example that we picked, x was a set of students. Phi1x was simply the Phi1x for us was simply the score of the students in the first two segments. Okay, Phi2x was the square of the score of students in the first two segments. Phi3x was the cube of the score of the students in the first three segments. We also have a Phi0x, which was just always 1. Okay, it's like a feature that's not informative, it's just always 1. Okay, so these theta i's represent the relative importance of feature I in predicting f of x. Okay. So that is the fundamental paradigm, and in this context you can simply construct the training error as summation of f of xi minus use a different parameter here, f of xj minus summation of theta I phi I xj. Okay, so this summation is over I equal to 1 to n, and this whole summation is over j, okay, equal to 1 to m. Okay, so m here is the number of training data points. Okay, and n here is the number of features. Okay, once again you see that whatever expression you have is linear in the theta i's. Okay, and then this can be solved using the linear least squares problem. Okay, so I'm not going to go into much more details in this, and in fact for this lecture I'm not even going to upload the usual notes, because this is not this is more of just to connect the concept that we have learned to something that you might learn in another course. Okay, I just wanted to lay the foundation of that bridge. More of these details, especially as it relates to how to pick the model, overfitting, how do you generate these features, how to engineer the features, and different other practical aspects will be covered in other courses. Okay, please do read chapter 13 from your textbook VLMS. That covers a lot of these concepts that I'm talking about and much more. Okay, in fact I would say that's one of the best written chapters of the book, especially if you want to see the connection of all these concepts to machine learning.